We're going to learn about exponents and roots, starting with exponents. When we say 2 to the power of 3, for example, what does that mean? This is an abbreviation. This is a short form that implies 2 has been multiplied by itself 3 times. So when 2 is multiplied by itself 3 times, we just pack that and show it like this. So if I use variables instead of numbers so that it could include any number, like a general formula, I say x to the power of n. So there are n x's that are multiplied by themselves. Now if I multiply two numbers by each other that each are raised to a certain power, for example 2 to the power of 2 times 2 to the power of 5, what will be the result of this? So let's expand this and realize we know 2 times 2, that's 2 to the power of 2 is 2 times 2 multiplied by 2 to the power of 5 is 5 times multiplied by itself. So 2 times 2 times 2 times 2 times 2. So 5 times here and 2 times here. How many times 2 has been multiplied by itself? We can show that by 2 to the power of 2 plus 5, or 2 to the power of 7. So now again, if I replace those numbers with variables, I can have a general formula. So let's say x to the power of a times x to the power of b. I can write that as x to the power of a plus b. But if the bases were not the same, for example, if I had 2 to the power of 2 times 3 to the power of 2, now I cannot do that anymore. The bases, or this number we call the base, must be the same so that I can apply this rule, right? Both bases here are x. So in this case, you just have to raise each number to that power. So 2 times 2 times 3 times 3. And then do the calculation. So this will be 4 times 9, or 36. What about when we divide two numbers that are raised to a certain power by each other? For example, x to the power of a divided by x to the power of b. What happens then? Well, let's expand this and see what happens. So x to the power of a, that means x has been multiplied by itself for a total of a times, right? And x to the power of b is x multiplied by itself for b times. Now of course we don't know what a and b are, but they could be any number.
The more the merrier.
So you realize that we can cross off these x's from the top and bottom. They get divided by each other. They're the same number. X divided by x, that's just 1. So for as many x's there are at the bottom, the ones at the top gets crossed off. So I can write this as x to the power of a minus b. For example, let's say you have 2 to the power of 3 divided by 2 to the power of 2. So 2 to the power of 3 is 3 times multiplied by itself, and 2 to the power of 2 is 2 times multiplied by itself. So these two at the bottom cancel with the top. This with this, that with that, and then the answer is just 2 to the power of 1. In other words, 1 is just 3 minus 2. So again, this formula, when you divide two numbers with the same base that are raised to a certain power, you just subtract the power. The base has to be the same again here. If the bases are different, you cannot apply this rule. How about when we raise a number that is already raised to a power? For example, let's say 2 pi squared. 2 pi squared. Now I raise this number to the power of 2. What's the answer? So let's assume now, let's consider whatever is inside the parenthesis. Let's call it capital X, uppercase X. So saying 2 pi squared to the power of 2 is like saying this capital X to the power of 2. Whatever is inside the parenthesis will be raised to the power of 2. So I can write 2 pi squared gets multiplied by another 2 pi squared, right? 2 pi squared is multiplied by itself how many times? 2 times. Great, let's do that. So you get 2 times 2, so that's 4, pi squared times pi squared. The bases are the same. The bases are pi, and we can add up the exponents together. 2 plus 2, that's 4. Let's see another example. Suppose you have 3a squared to the power of 3. What does that mean? Again, that means that everything that is inside the parenthesis is raised to the power of 3. So 3a squared times 3a squared times 3a squared. That how many times? 3 times, right? So let's do the multiplication. Here we have a, the bases are the same, so we can add up the exponents of the a. So, and we can do the same for 3. 3 are getting multiplied by each other. Each has a power of 1. They have all the same base, so we can add up the exponents of the 3. So 3 to the power of 3, a times 8 to the power of 2 plus 2 plus 2, that's 6. So that's the answer. There's a shorter way of getting this final answer here. I can say this power of 3 that is outside of parenthesis, I can just multiply it by the powers of what's inside the parenthesis, by those exponents. So 3a squared to the power of 3, I can immediately say the answer is 3 to the power of 3 is 1, so 3 times 1, that's 3. A to the power of, already it had a power of 2, so 2 times 3, that's 6. So I can even write that as a general rule by saying x to the power of a and multiplied by y to the power of b. If all that is raised to the power of n, what's the result? Again, we influence that power outside of the parenthesis into whatever is inside the parenthesis. We multiply by the exponents. So it turns into x to the power of a times n times y to the power of b times n. Now, it doesn't matter how many layers of powers you had. What I mean by that, x to the power of a, suppose it's 1 time raised to the power of b, and again, 1 time raised to the power of n. So we start from outside and we delve deep into the parentheses. So we say x to the power of a to the power of b is raised to the power of n. So I can write x to the power of a to the power of b times n, just like above. Now once again, we want to influence this power into the parenthesis. So it becomes x to the power of a times b times n. What if you had negative exponents? For example, what does that mean? 2 to the power of negative 3. So that's a code, and we need to find the meaning of it. So it's a convention that we make. So whenever you see a negative exponent, you can turn it into a positive exponent, but first you need to bring the base into the denominator. So you make a fraction. I mentioned the base as the denominator, and as the numerator you can just put 1, and then the power of 2 here, or the power of the entire parenthesis, will be just positive 3. So 1 over 2 to the power of 3. That's the meaning of negative exponents. Again, let's say you have 4 to the power of negative 5. What does that mean? Same thing, 1 over 4 to the power of positive 5. So that's the definition of having a negative exponent. So we can generalize that with use of variables. X to the power of negative n is equivalent to 1 over x to the power of n. I can put the power here, the denominator, or I can just put the power in the entire parenthesis. Doesn't make any difference because the numerator is just 1, and 1 doesn't matter how many times gets multiplied by itself, the answer would be still 1. And the reverse of it is also true. Let's say you had a number 1 over x to the power of n. You can bring the x to the numerator, so you say x, but flip the sign of the exponent, x to the power of negative n. So it's kind of going in reverse here.
Shifted in reverse.
Whenever you flip the sign of the exponent, you have to reciprocate the base. If it's in the numerator, you can put it in the denominator, and vice versa. So if I have a fraction that has a numerator x to the power of a over y to the power of b, I can write that as x to the power of a times y to the power of negative b. I now bring the y to the top. From the bottom, I flip the sign of its exponent. Or you could bring x to the denominator. So you can say y to the power of negative b over x to the power of negative a. Or you can keep both of them in the denominator. So you say 1 over x to the power of negative a times y to the power of positive b. This was originally in the denominator. You keep it as positive b. So you can play with these in order to simplify any algebraic equation. Let's now learn about roots. So what roots are? You must have heard of square roots, for example. Square root of 4 is 2. Square root of 9 is 3. Let's examine this more closely. So square root of 4, what is 4? 4 is 2 times 2, or 2 to the power of 2. So square root of 2 to the power of 2 became 2 to the power of 1. Square root of 9, what is 9? 9 is 3 to the power of 2. So square root of 3 to the power of 2, the answer is 3 to the power of 1. Similarly, square root of 16, for example, is 4. 4 times 4 is 16. So looks like square root of 4 to the power of 2 again equals 4 to the power of 1. So it looks like what square root does is basically it halves the exponents. A square root is like saying, let's say a square root of x to the power of a is like saying x to the power of a over 2. What about cube root? Let's say cube root of 8. So we have a concept of cube root. We put a 3 here, and that's called the degree of the root. Degree of the root is 3, and we call it cube root. Or you can say third root, right? Instead of square root, you can say second root. Cube root, you can say third root. Fourth root, you can go to whatever. So cube root of 8 is what? We know 8 is basically 2 to the power of 3, right? 2 times 2 times 2. And with a degree of 3, third root of 2 to the power of 3, it plays the same function. It, instead of halving the exponents, now this time, divide the exponents by 3. So 2 to the power of 3 over 3, or just 2 to the power of 1, which we can write just as 2. So roots in general, they have a degree. For square roots, when we don't mention anything here, that means the degree is 2.
It's a secret.
But we don't mention it. So square roots, that means degree of the root is 2. So square root with a degree of n, again generalizing this concept with variables, square root with a degree n, and under the square root, let's say you have x to the power of a. The answer is x to the power of a divided by the degree of the root, divided by n. For any root, you apply this formula. If you had like multiple terms inside the root, what about then? So for example, square root of x to the a times y to the b, or not square root, just any root, nth root, x to the a times y to the b. What do? You can first of all separate this into nth root of x to the a multiplied by nth root of y to the b. And then separately you can say that is, the first term is x to the power of a over n times y to the power of b over n. So the degree of the root is what goes to the denominator of that exponent. What if you have some roots divided by each other? For example, root nth root of x over nth root of y. You can first of all mention that as a one root, nth root, x over y, and then calculate it. What if you had multiple roots on top of each other? For example, here you have x, you take nth root here, and then from on top of that you have m root here. So let's do it step by step. First I separate from inside, we go outside. So the nth root of x, I can write it as x to the power of x here is 1. So 1 over n, x to the power of 1 over n. And then do the same one more time. So x to the power of 1 over n. Now we take the mth root. That gives us x to the power of 1 over n over m, which is equivalent to x to the power of 1 over n m. Let's see some examples. For example, suppose you have square root of 2, but not just once, twice, thrice, and 4 times. And then that entire thing to the power of 48. What's the answer to that? Okay, now let's start from inside and build up on top of it. So the first square root, I'm gonna put a green circle around it. So instead of that, I'm going to write 2 to the power of 1 over 2. That's what it means, right? So now I include the rest of it. So I have 3 more roots, 3 more square roots. So I put them 1, 2, 3. And then all of it to the power of 48. Let's go one step further. Now this one, I'm gonna put a red circle around it and deal with it. So that means you get 2 to the power of 1 over 2 over 2. Again, gets halved again. So 2 to the power of 1 over 4. How many square roots I have left now? 2 more. 2 more square roots, and all of this to the power of 48. Excellent. Let's do that one more time and put a circle around what am I dealing with now in this step. So 2 to the power 1 over 4 again gets halved. So 2 to the power of 1 over 4 divided by 2, it becomes 1 over 8. How many square roots I have left? Just 1. This gets to the power of 48. Let's deal with it one more time. 2 to the power of 1 over 8 gets halved again. The exponents gets halved. So it becomes 2 to the power of 1 over 8 over 2. That is 1 over 16. And this gets multiplied by 48. Now I apply that rule that says x to the power of a to the power of b outside of parentheses is like saying x to the power of a times b. So using that rule here, we just need to multiply the exponent outside of the parentheses, 48, by 1 over 16. So it becomes overall 2 to the power of 48 over 16. And you can simplify that exponent further. For example, you divide the 2 by each other. So that's just like 2 to the power of 3. Result of that fraction, that division. 2 to the power of 3 is what? Is like 2 times 2 times 2. And that is 8. So that's the answer to this. Let's see another one. Suppose you have square root of 4, or actually cube root of 4, and then square root of that. So what is this? Let's simplify it. Starting from within, I'm going to deal with this cube root now. So 4 to the power of 1 over 3. That's the meaning of that cube root. 4 to the power of 1 over 3. Now I have one more square root on top of that. So now the exponent 1 over 3 gets halved again. So it becomes 4 to the power of 1 over 3. If it gets halved, multiplied by 1 over 2 to get half. That means 4 to the power of 1 over 6. Can I simplify that further? Yes, I can. I can say instead of 4, I can say 4 equals 2 to the power of 2, right? So instead of 4, I mentioned 2 to the power of 2. And then 2 to the power of 2 is raised to the power of 1 over 6. So again, we can multiply the exponents here. I can say 2 to the power of 2 over 6. I just multiplied 2 by 1 over 6. Can I simplify the exponent further? Yes, that's like saying 2 to the power of 1 over 3. In other words, 2 to the power of 1 over 3, that's like cube root of 2. So that's the answer. Let's see another example. Suppose you have square root of 2 over square root of 6, and this gets multiplied by square root of 10 over square root of 45 to the power of negative 1. Let's simplify this one.
Look at this beast.
First of all, all of them are square roots here. So the first square root of 2 over square root of 6, I'm just going to write it like this. One square root, one big square root, 2 over 6. I can do that, right? Now the second one here, to the power of negative 1. Remember the negative powers? We can just flip the sign if we reciprocate that fraction. So whatever is on the top here, I'm going to put the parenthesis. Square root of 10 was on the top, I bring it to the bottom. Square root of 45 is at the bottom, I bring it to the top. And just flip the sign of the exponent. So negative 1 becomes positive 1. Or you can just not write it because the power of 1, we don't even include it. And again, this I can just write it as one big giant square roots, 2 over 6. And then the other, put both of them under one square root, 45 over 10. Or put all of them under one square root, 2 over 6 multiplied by 45 over 10. Why? How come I could do that? Because the degree of these roots were the same. They both were square roots, second degree roots. Okay. So now let's just simplify these numbers, normal fractions. So I can say 2 divided by 2, that's 1. 10 divided by 2, that's 5. I can say 5 divided by 5, that's 1. 45 divided by 5, that's 9. I can say 6 divided by 3, that's 2. 9 divided by 3, that's 3. So overall, I got square root of 3 over 2. Or square root of 1.5. So let's just summarize here the rules that we learned. First of all, the definition of root, when we say x to the power of n, that means x gets multiplied by itself how many times? N times. If the bases are the same, two numbers multiplied by each other, x to the power of a times x to the power of b, you can add up the exponents, say x to the power of a plus b. If they're divided by each other, for example, x to the power of a divided by x to the power of b, you can just subtract the powers, say x to the power of a minus b. And in fact, we are already using the concept of negative exponents, because here you have written x to the power of a. Now you wanted to bring x to the power of b to the top, so you flip its sign. You say times x to the power of negative b. And once again, you use the previous rule, and you say the bases are the same. I just add up the exponents. So x to the power of a plus negative b. In other words, x to the power of a minus b. So essentially, it's the same rule. If stuff in a parenthesis, like x to the power of a times y to the power of b, is raised to a certain power, that power gets influences all of those terms inside. So it becomes x to the power of an times y to the power of bn. You can reciprocate a fraction, x to the power of a over y to the power of b. You can write it as x to the power of a times y to the power of negative b. Here you cannot say x to the power of a minus b. You cannot just subtract the powers because the bases are different. You can just like bring a term to the top, flip the sign of it, and in reverse. I can even bring x to the bottom and say 1 to the power of say y to the power of negative b over x to the power of negative a. Or bring both of them down and say 1 over x to the power of negative a times y to the power of positive b. And now we arrive the concept of root. So x to the power of a, taking the nth root of that, means you divide the exponent of x by n. So x to the power of a over n. And if you had multiple roots with the same degree, for example, x to the power of a, nth root of that, times y to the power of b, nth root of that, you can just write that as one nth root and multiply those two together, x to the power of a times y to the power of b. Similarly, you can do that for a division of the roots. So nth root of x over nth root of y is equal to one big nth root x over y. So using these rules, you can simplify algebraic terms and solve your problems that you encounter in physics or chemistry more efficiently. Hope you enjoyed it. Let me know what you think or if you have any questions.